Hi again, and welcome to part one of the stochastic simulation introduction module. So in this section, we'll be thinking about discrete time methods, and in particular, we're going to think about Reed-Frost models. So a quick reminder on deterministic versus stochastic methods, since we're going to be looking at both types of the Reed-Frost model, a deterministic version and then the stochastic version. Deterministic is a population update that's based on the expectation or average, versus stochastic, where the population update will be based on a binomial draw. And we'll hear a lot more about this. But you may have heard of chain binomial models, and that is an extension of the stochastic version, where we iterate this draw from a binomial distribution, and that iteration gives us the chain of binomials. But we'll hear a lot more about that. So moving on, so the basic Reed-Frost model definition. So in its most basic form, there's a fixed infectious period duration, and generations of infectious individuals don't overlap. So what this means is that if an individual is infected at time t, by time t plus 1, they are recovered. So you have these cohorts, groups moving through time, and you don't have anyone that was infected at a different time in the same cohort. Or the same generation. So for this model, we're going to define P, the probability of infection given exposure, I sub T, the number of infectious individuals or cases at time T, S sub T, the number of susceptible individuals at time T, and R sub T, the number of recovered individuals at time T. So how should we determine the number of individuals in each of these groups at time t plus 1? Well, for each susceptible individual at time t, we're going to build this up piece by piece. So we have P, the probability of getting infected. So 1 minus P is the probability of not getting infected by a particular infectious individual. But in order to not get infected at all, we have to raise this to the number of infectious individuals. So 1 minus P to the IT is the probability of not getting infected by any infectious individual at time t. And then again, 1 minus that value then is the probability of getting infected by any infectious individual. So for simplicity of notation, we're going to let Q equal 1 minus P, and then just subbing that in, we have that the probability of getting infected by any infectious individual is 1 minus Q to the IT. So that's what this says. And then we use that probability to find the expected number of cases in the next time unit. So the number of infectious individuals or cases at time t plus 1 is the current number of susceptibles times the probability of getting infected by any infectious individual. And we also need to update our other state variables. So the number of susceptible individuals in the next time unit is the current number of susceptibles minus the number of new infections. And since we have the non-overlapping generations, recovered individuals in the next time unit, RT plus 1 is the current number of recovered individuals plus the number of individuals that were infectious at that time. So we have the full set of equations oriented in the way that we're most familiar with in this course. And one way to check our understanding of the model is to think about the basic reproductive number. So the basic reproductive number, just as a reminder, is the expected number of new infections caused by a single infectious individual in an otherwise fully susceptible population. So how can we think about that for this model? Well, I sub t plus 1 is the number of new infections in a time step. If we have a single infectious individual at time t, this is 1. And then what about S sub t? Well, if n is s plus I plus r is the total population size, and we said that there's one infectious individual, and it's an otherwise fully susceptible population, that means we have 0 recovered individuals. So S equals n minus 1 equals S. So we can plug that in for ST, and we get, so we can plug that in for ST, n minus 1, and we sub that I sub t was 1, and we get that the number of new infectious individuals the basic reproduction number is n minus 1 times 1 minus q, or n minus 1 times p. So here I have shown a simulation of the deterministic Reed-Frost model for a reproduction number of 1.5. So we can plug that in for ST, n minus 1, and we sub that I sub t was 1, and we get that the number of new infectious individuals the basic reproduction number is n minus 1 times 1 minus q, or n minus 1 times p. So here I have shown a simulation of the deterministic Reed-Frost model for a reproduction number of 1.5. So you see this outbreak and this result. So starting with this initial value and the parameters required for R naught to be 1.5, or so the probability of infection that results in R naught being 1.5 will always give this trajectory. Hence, that or as a result of being a deterministic model. So for the next step, we want to incorporate chance. So if you call the binomial distribution here, we can let P be the probability of getting tails on a given flip, and then think about each of these parts. So this factor in the front, the binomial coefficient, is the number of ways to get k tails with n trials, and then p to the k is the probability of getting k flips all landing tails, but then we need the rest of the flips to be heads. So we multiply by the probability 1 minus p to the n minus k. And this gives us the probability of getting k tails. But we can also think about this as a infection model. So instead of letting P be the probability of getting tails on a given flip, let's think of P as the probability of a susceptible individual getting infected. So now we have same binomial expression, but with different components. We have the probability of X individuals getting infected by any infectious individual in the middle. And then we need the rest of the susceptible individuals not to get infected. So we have the probability of S of t minus X individuals not getting infected by any infectious individual on the right. And then we have that binomial coefficient for the number of ways to choose X individuals out of the susceptible population at time t. And then again, we have our update equations for our state variables. So the number of susceptibles in the next time step is the current number of susceptibles minus the new infections, and the number of recovered individuals in the next time step is the current number of recovered individuals plus the new infections, or the current infections. So we've talked a lot about the basic Reed-Frost model, but how do you simulate it? Well, one way to start thinking about generating a simulation is to write down pseudocode. So this is an example of pseudocode, and it's a way to lay out the general plan for your simulations without writing down all of the detail that you would have in your operational code. So for the Reed-Frost model, at first we will define our initial conditions, and then we have this while loop that has some dependencies. So in order to keep our simulation running, we want both the number of infectious individuals to be greater than 0, and if we want our simulation to stop, we can define a max time that we're willing to wait for the simulation to end. And then our simulation will check whether the current time is less than that maximum time. And if not, it will stop and give us our results. But while these two conditions are met, we will calculate the number of new infections, update our state variables, SI and R, and update the time. And then this will keep repeating while these two conditions are satisfied. So here on the right, we have the deterministic model that you've seen previously. And then on the left is the stochastic Reed-Frost model of a few simulations where the element of chance has been incorporated. So we're seeing these different trajectories, even though they're based on the same expected R naught equals 1.5. And this figure was produced by a tutorial that you can access on the ICI3D R tutorials collection for chain binomial models. So let's think about chain binomial models in general. So we can also formulate these to allow for overlapping generations of cases. And we do this by, instead of having the generations or cohorts of infectious individuals all move together to be recovered after a time step, to have a probability of recovery on each time step. And we can call this probability of recovery R. So for any infection or any individual who is infectious at time t, the probability of recovery by time t plus delta t is R. And this leads to a little bit more complicated model, but we have X and Y are random variables for the new infectious individuals and new recovered individuals. Random variables are definitely worth a course on their own, so I won't get into what that means. But there is a probability associated with the different values of X, as we can see in our expressions for the probability of getting X individuals and the probability of getting Y individuals using our probability of infection P and our probability of recovery little r. And similarly to our other update equations, we're going to have T plus delta T as our new time. And now we will subtract X, the number of new infectious individuals, and for the number of infectious individuals at the next time step, we start with the current number of infectious individuals, add the new infectious individuals, and subtract the recovered individuals. So then the number of recovered individuals at the next time is the current number of recovereds plus the newly recovered individuals. And we can think about these chain binomial models using the same parameters that we used in the ODE models. To do that, as we have done already, we define the instantaneous hazard of infection for an individual, susceptible individual, as beta I over n. And we can use this in our definition of the probability of infection by having 1 minus e to the minus beta I over n times delta t. And this comes from waiting time distributions, which we'll talk a little bit more about in part 2. But the probability of infection essentially is 1 minus the probability of remaining susceptible after a time delta t. And then similarly, for an infectious individual time t, the probability of recovery by time t plus delta t is 1 minus e to the negative gamma times delta t. So I'm showing another example of pseudocode here. It looks similar with minor adjustments. So again, define the initial conditions at the beginning, and then there's a while loop while we're meeting those conditions of having infectious individuals still around and we haven't hit our maximum time. We calculate the transition probabilities, which are state dependent, as we see. So it depends on I here for the probability of infection. And then we determine the number of transitions for each type. So here, the number of infections and the number of recovery events. And then we update our state variables and update the time. So that is the end of part 1 on discrete time models, and I'll see you shortly for part 2 on event-driven stochastic simulations.